So I'm starting the lecture. Uh, Today we are going to see about the how to design the processor. Basically, that we are going to learn that which are the functional hardware component used in the designing of the processor, right? And it is this particular process is known as the building data path. Okay, so the things that we are going to discuss in today's lecture is that which are the functional hardware used, okay, and what is the convention behind those functional hardware. Then we will understand how to design the data path, and we'll be designing a simple implementation scheme related to data path. Now, this is the logic design convention that in a processor, we are having two types of elements which are known as the combinational elements, and another one is known as the sequential elements. Right? The main difference between these two elements are the combinational elements does not preserve the state. That means it is not able to store any value in that. The purpose of combinational element is just to process the data or process the input, whereas the purpose of sequential element is that it can process as well as it can store the data. If I would be giving the example of the combinational element is like ALU, right? That ALU is supposed to perform some arithmetical and logical operation like your AND gate, OR gate, all are known as the combinational elements. Whereas the sequential elements, that means that the registers that we have, the memory that we have, that all those elements are known as the sequential elements, right? Basically, these two elements, we don't require that much understanding of those two elements. Just we have to keep in mind that there are two types of element, like combinational element and the sequential elements. Okay, so here again there is these are the some examples of the combinational elements like AND gate, the adder, multiplexer, and ALU, right? And see, we are going to use that adder, ALU, as well as multiplexer. Okay, so here in this multiplexer you can see that there are two inputs, right? And based on that, based on the value of these two inputs, right, the output would be selected. Okay, and this here you can see that this is the programming logic, that how the multiplexer is implemented. For the ALU, if you see that ALU would always take two inputs because all these are binary operation. All the processor follows the binary operation. So here also that ALU takes two input, input A, input B, and produce one output. Okay, and also sometimes ALU sets some flags, certain flags, right? So here you can see this is the output of the flag. Similarly, we are having adder, right? That adder takes two input and produce one output. Okay, obviously the adder is not supposed to produce only one output, it produces two output, that is the summation as well as the carry bit. Okay, so basically so far the processor which we are studying, which is known as the lag version 8, okay, in that we have studied so many types of instructions, but here basically we are going to discuss about the three types of instruction. Those are the memory reference instruction, arithmetic logic instruction like add, subtract, and or instruction, and the instruction related to the comparing and branch instruction. Okay, so we are going to design the data path based on three different types of instruction. Okay, so now the first thing that we are going to understand that what happens that when we start executing our program. So if you can recall that whenever we we start or we write any program and we compile that program gets stored into the hard disk, right? That is our hard disk. Okay, so consider this is our hard disk. Okay, see, please bear with me drawing as I used to say to you. Okay, so consider this is the hard disk where our program would be there. Okay, consider here we are having a program. Now when you start executing that program will go into the main memory, right? Consider this is the main memory, and here these are the various slots, blocks of the main memory. Okay, this individual block contains the instructions. Like here we would be having instruction 1. Okay, here we are having instruction 2. Okay, here we are having instruction 3. Okay, then we are having instruction 4. This is how my program will be stored in the main memory when I will start executing the program. Okay, now here we are going to have a processor. Let's see, where is the processor? Here is the processor. Okay. Okay, so to run the program, processor requires to fetch the instruction from this particular location. Okay, so what processor will do? Processor has one specific register which is known as the program counter register. Okay, so consider this is the program counter register. Okay, this program counter register would be having the address of the next instruction which is going to be executed by the processor. Now, as we know that this particular memory, which is known as the, let's say that is a RAM, okay, or it could be cache. Okay, but right now for the sake of simplicity, sake of understanding, we are taking the simple case. Consider that we are having our program or instruction in the RAM. Okay, so obviously all the instruction would be having some address. Let's say that this particular instruction is stored at the memory location, let's say 44. Okay, so when you start executing your program, at that time that processor's program counter register would be initialized with the value 44. Okay, like this. Okay, so processor will get idea that I require to fetch the instruction from the memory location 44. Okay, so processor will request to the block number 44 that give me the instruction which is stored at the memory location 44. So once the instruction would be fetched from the main memory to the processor, at that time that instruction would be stored in one particular register which is known as the instruction register, IR. Okay, IR, like this. Okay, and here this would be having instruction. Okay, now the size of this particular instruction register is how many bit? Can you recall? It is 32 bits. Okay, 32 bits. Please mute your mic. Please mute your mic. Okay. So this particular process, that whatever we have done, that the processor is fetching the instruction from the main memory to the register called IR, is known as the instruction fetch phase. Okay, so this is one of the part of the instruction execution. Okay, so like this there are so many part of the instruction execution, so that is what we are going to see now. Okay, so I require to remove all this. Okay, so the first phase is that we are having a fetch phase. In that, what happens that, please mute your mic. Uh, what is going to happen that the instruction is going to be fetched from the main memory to the processor. So here you can see that the memory would be accessible with the help of the address of the program counter. Okay, and whatever instruction would be fetched, that will be stored inside the register which is known as the IR. The same time, what is going to happen that as the first instruction has been fetched, okay, so next time processor requires to execute the next instruction. Okay, so for that the program counter value should be incremented by 4 in that case, because we consider that the size of block is 1 byte. So obviously that to store one particular instruction in the memory, it requires total 4 different blocks, because the size of block is only 1 byte. So 4 blocks would be used to store one instruction, and that's why the value of program counter should be incremented by 4. Okay, so in as per the previous example, the first instruction was having the address 44. So for the next instruction, that address would be which one? 48. Okay, because the instruction gets stored sequentially. Okay, so this is the first phase of the instruction execution, in that the instruction requires to be fetched from the main memory to the register. The next thing is that once the processor would be having that instruction in the register IR, after that processor requires to understand that what I supposed to do with this instruction. Okay, and from where I require to fetch the operand to perform the operation. Okay, like suppose consider that the instruction is add instruction. Okay, so obviously that once the processor will get the idea that I require to perform addition. Okay, but to perform addition, processor requires two input. Okay, so how processor will get the idea? The processor will get the idea based on the instruction which is available in the instruction register. Okay, so if you can recall that in the lecture of instruction set architecture, at that time we had seen that every instruction has some format. Like consider the add instruction has format. Okay, size of add
Hello, wait,
instruction,
Papa Dara.
please mute your mic. Size of this instruction is 32-bit. Okay, now this whole 32-bit, it's divided into number of fields so that the processor can understand that what to do with this instruction and how to fetch the operand values. So let's take the example of the add instruction or ALU instruction. Okay, add instruction. Okay, so in add instruction, what happens that the first 11 bits are opcode that specify that what is the operation, what is the type of operation. So first 11 bits have been used for the opcode. Next 5 bits are used as one of the source. Here I am writing the number of bits because I am not having space. Okay, so this is the source 1. Okay, then next 6 bits, how many bits? 6 bits. It's for the shift wing value. Okay, and this particular field is not used with the for the add operation. So in that case of add, this value is always going to remain 0, or for any logical operation or arithmetic operation, this particular field is going to remain 0. The next one is the source 2. Okay, source 2. Okay, and this is also 5-bit field. Okay, and this one is the destination field. Okay, and this is also 5-bit. Okay, now I think it is clear to all of you that why do we have only 5-bit field, that is a source 1, source 2 and destination, because here in this processor we know that there are only 32 register, and to locate one of the register from this 32 register we require only 5-bit, that is 2 raised to 5, that is equal to 32, and that's why we are having only 5-bit. Okay, so such kind of thing would be there in the register, which is known as the instruction register. So what happens that once the instruction will go into the instruction register, at that time the processor will start the decoding of the instruction. Okay, so what processor will do? First, processor will try to look into this particular opcode. Okay, this opcode would be having total 2 raised to 11 different values. Okay, and based on this 2 raised to 11 values, that processor will get idea that what operation I supposed to perform, and what operation I supposed to perform means that which uh, electronic circuit that I have to activate to perform this particular operation. Okay, once that is found, that which operation is supposed to be performed by the processor, what will happen that the processor will get idea that which registers I have to use as an input. Like see, S1 and S2 both are providing the register register numbers, like this is the input 1 and this one is the input 2. Okay, so here this will give the idea, these 5 bits and these 5 bits are giving the idea that which register is having the input value. Okay, and this 5-bit will give the idea that where I supposed to write the final result, or in which register I supposed to write the final result. Okay, so this particular operation is known as the decode operation. Okay, so this is decoding the instruction and get its operand. Okay, so this particular unit, the hardware which perform this, is known as the decode unit, and basically the control unit does all this thing. Okay, so it has two operations, that is decoding the instruction. Okay, and obviously this would be carried out by the logic circuitry, and the second one is that getting the operand from the register, that is the register access. Okay, so this is the second this one is the second operation or second phase of the instruction execution. So far we have discussed about the first phase. This is the first one and this one is the second. The first phase is the fetch instruction, that means fetching the instruction from the main memory to the register called IR. And the second one is the decoding, that means understanding the instruction and getting its operand locations. Okay, now we are having a third phase, that is the execution phase. In this phase, what will happen, that whatever operation has been specified by the instruction, that would be carried out by the ALU. Okay, so in this case, what will happen, that the control unit will trigger the appropriate functional hardware, so that suppose if the operation is OR operation, at that time only the OR gate or OR circuit would be activated. Okay, at that time we don't require to activate the adder, we don't require to activate the multiplier, etc., etc. Okay, so control unit knows that I require to activate only the that OR circuit. Okay, rest of the circuit I don't require to activate. Otherwise, what will happen, that the if the control unit will activate all the circuit now, that then all the circuit will produce some output, and at that time that would be difficult to find out that what is the correct output. Okay, so this is the third phase of the instruction execution. The first one is the fetch phase, the second one is the decode, and the third one is the execute. The fourth phase is that suppose that the instruction is the load instruction or the store instruction. So in that case, what happens, that the whatever like data is there in the register, source register, that should be written to the main memory. Not main, I should not say main memory, but it would be stored in the memory. Okay, and if the instruction is stored, in that case, what will happen, that whatever is there, whatever data is there in the memory, that should be returned to the destination register, and this particular phase is known as the load or store operation, right? And basically we know that the RAM is like to access the RAM is quite expensive in the case of processor, and that's why we are having a cache. So basically what happens, that the load and store would be performed with the cache memory only. Okay, and the last phase of the instruction execution is known as the write back phase. In that, what happens, that whatever output would be produced by the instruction, that would be written back to the destination register, and this particular phase is known as the write back phase. Okay, so the thing that we have to keep in mind, that for all these 5 different phases, we are having a separate hardware in the processor. Okay, so hardwares are not overlapping with each other, right? Obviously you must be having a confusion that the memory is used over here, okay, and also it is used over here. Okay, so you may consider that the memory is overlap, right, in this phase as well as in the load and store phase, in the fetch phase as well as in the load and store phase. Okay, so but what basically happens in the modern processor, what we have, that there are 2 different types of caches available in the modern processor. One cache is known as the write cache, and the another one is cache, sorry, it is not write cache, but it is known as the like data cache and instruction cache. Okay, so every processor, the modern processor, every modern processor has 2 types of cache: data cache and the instruction cache. Data cache would be storing the variable which we might have declared in the program, whereas the instruction cache would store only the instruction related to the program. Okay, so now it may be clear to you that in this particular phase, which cache must be used? Instruction cache. Okay, this particular phase is using I cache. I cache. I cache. Okay, and this particular phase is using which cache? Data cache. Data cache. Okay, so there are 5 phases of the instruction execution. That is the fetch phase, where the instruction would be fetched from the main memory to the register IR. Then the instruction required to understand the processor required to understand the instruction, and this would be happening in the decode phase, where not only that the processor will understand the instruction, but also the processor will find out that where the operands would be, or from where the input will come. Okay, The third phase is that the execution of the instruction, in that the ALU would be involved and particular appropriate circuit would be activated. The fourth phase is the load and store phase. In that case, what will happen that the memory would be accessed either for the reading or the writing. Okay, and the last phase is that write back phase. In that phase, that the result would be returned back to the destination register. Okay, now how can I build the fetch unit? Okay, which functional hardware component I require to build the fetch unit? So obviously I know that I require to have the instruction address where it is stored in the memory. Okay, so for that I require program counter, and obviously to store my program I require the memory, right? So this is what you can say, that instruction memory. And as I told you that basically in the modern processor, this is what I cache. Okay, so this instruction memory would have one that input and one output. That input would be the address of the instruction that would come from the program counter. Okay, and this particular port is output port. What it will do, that it will put the instruction into this particular data line. Okay, and also we require adder, because what happens that once the instruction had been fetched from the main memory, okay, what should happen, that the value of PC should be incremented by 4, and that's why we require adder. Okay, so here one of the input would be the previous value of PC and another value would be 4. Okay, so that this output would be what, PC plus 4. Okay, so this is the fetch unit. Okay, how it would be rearranged. Okay, so here you can see this is how it would be rearranged. Okay, so this is a PC program counter value, that is 32-bit register. Okay, it would be having 32-bit value. Okay, this value would go over here, right? That is the read address, that which instruction we want to read from the memory. Okay, and this is going to activate one of the block. Okay, so the output of the block would be written over here. Okay, and that will be used by the next hardware component. Okay, which is there in our processor. Okay, and along with that, what will happen, that the value of PC is going to be incremented by 4, as we have seen in the previous slide. Okay, and this whatever output would be generated, that would be written back to the program counter. And please don't consider this is a write back operation. This is not a write back operation. Okay, yeah, so this is the fetch unit. I hope this is clear to all of you. If you have any question, you can ask me. Any question? Okay, no problem. If there are no questions, I'm moving ahead. Okay, so next one is that how to build the decode unit. Okay, so here we know that there are total 32 registers where we have in our processor. Okay, so the registers are stored in a file which is known as a register file. Register file is nothing but it is a pile of registers that we have, or stack of the register that we have. Okay, now here you can see that what happens, that like if we consider the add instruction, so add instruction, there are two operands. Okay, so obviously in the register file here you can see that I have to specify two input. This is the first one and this one is the second input. Okay, so read register 1 and read register 2. Okay, so from where this particular value will come, so if you can recall that the instruction architecture that I have explained earlier, okay, that every instruction would have ALU type of instruction I'm talking about right now. The ALU type of instruction, ALU type of instruction, the first 11 bits are opcode. Okay, first 11 bits are opcode. The next 5 bits are source 1. Okay, next 5 bits are source 1. So this particular 5 bit will go over here. Okay, right? Then we are having a shift value. This is always going to remain 0 in the case of ALU. And the next again 5 bits are source 2. Okay, so this will go over here. This one, this will go over here in the read register 2. Okay, and we know that in decode field this happens, that processor knows that the after 11 bit, that whichever next 5 bits are there, these are the source 1, and after the 6 bit, that next 5 bits are the source 2. Okay, and then we are having remaining 5 bits, then remaining 5 bits are the address of the write register. Okay, Is this clear? Okay, so let me erase all these things so I can show you something more. Okay, so in this register file, these three things are clear, that read register 1 port, read register 2 port, and write register port. Okay, along with that we are having the write data port, and this particular port would be used in the phase of write date. Okay, so whatever output would be generated after completion of operation, what will happen, that result would be returned to the write data. Okay, and these are the two output ports that we have. Just a minute, let me extend my time.